Hello, ladies and gentlemen. Welcome to Physics 20, Chapter 3, Forces, Lesson 1. Now, today, Introduction to Forces, we're looking at dynamics, why things move. Now, force is a push or a pull. You know about that. You've pushed stuff, you've pulled stuff. You all have little brothers and sisters or friends or cousins or uncles or someone who's pushed or pulled you. Now imagine you're sitting in a chair and someone pushes you. Well, if two people are pushing you, these forces add up, and you get the net or the sum of the forces adding together. Now notice I'm saying F net. Sometimes I will say force total. But I don't often use force total. I'm supposed to use force net. Anyway, now, if it's a tug of war, two people pulling against each other, the net forces can cancel out and be zero. Okay? Now, here, notice sneaky shortcut, a free body diagram, FBD. Now, here the object's a dot. So, here I am pushing somebody down the hallway on the chair. The object, that entire drawing becomes this red dot, and the forces are arrows going away from the object. Right? So that's the level of artistic skill I expect. Now at this point, I'm going to pause the recording because there's a free body diagram lab. Now of course you guys can't do it at home, but you guys will read through the lab and be prepared to do it when you come back. Alright? So take a minute, pause the recording, take a minute, read through the free body diagram lab, and then come on back. Welcome back. Now, the two things I want to talk about today, besides the free body diagram, are Newton's first law. Sir Isaac Newton, yes, famous physicist, 3 laws. We're going to talk about 2 of them today. The first one, if no net force acts on an object, comma, it maintains its state of rest. So if F net is 0, velocity is 0. Example, some guy standing there, one of you sitting there with your cell phone out playing with it instead of paying attention to me. There's no net force acting on you, your velocity is 0. Alright? Now be careful. If no net force acts on an object, it maintains its state of rest or constant movement. If F net is 0, the velocity will stay constant. For example, a spaceship out in space, it's drifting, there's no forces acting on it, so whatever speed it has, it will remain constant. So because velocity is constant, acceleration is 0, it's not speeding up, it's not slowing down. Now, that's fun, but there's no calculations involved. So we move on to Newton's second law. Now, if F net does not equal 0, the object accelerates in the direction of the net force. So here's Mr. Sutton pushing his car. It died, and he's pushing it. Now, Newton's second law, F net equals ma, where m is mass in kilograms, a is acceleration, meters per second squared, and F is the force in newtons. That's a new unit named in honor of Sir Isaac Newton. It's kilogram meters per second squared, mass times acceleration. Now, one little thing. Quite often, Newton's second law is written like this: acceleration is net force divided by mass. You'll see that a lot. Okay? So as a matter of fact, for this right here, I can ask, what's the acceleration of the car? Well, acceleration is F net over mass, which is 300 newtons, divided by 985 kilograms. Sorry. Now I do the math, pull up Mr. Calculator, and .304 meters per second squared. Okay? Now, so far so good? And that's almost as bad as it gets. because I'll use this and then its information in another calculation. So Mr. S's car dies on the road. If he has to push it 35 meters to get it off the road, how long does it take him to push the car off the road? What do we got here? Force, mass. We can calculate acceleration. So what we have here, the initial, the final acceleration, displacement, time question. Except this time we have to calculate the acceleration. Now, Mr. S's car dies on the road. If he has to push it 35 meters, that's D. What's the time? Now, notice the calculation, we calculate the acceleration we calculated, 0.304, 305, 304. If it dies by the side of the road, what's my V initial? 0. Okay? Now, we don't have V final, so offhand displacement is V initial T. It's 1/2 AT squared. Because we don't have V final, we don't want it. That's the only question without V final. And we plug in the numbers and solve. Now, normally I wouldn't like doing this because it's a quadratic, but with V initial 0, okay, and 35 meters equals 0.152 meters per second squared times time squared. I divide both sides by 0.152 meters per second squared. And I can't do that in my head anymore. And what do we get? $230. Now that's time squared. I screwed that. Screwed. Answer: 15 seconds. Well, if you want to get picky, I normally go to 1 decimal place, 15.2 seconds. All right. So far so good. Notice we're just calculating acceleration now. Now, of course, that means we can calculate the acceleration and then figure out the force. So this is just an extension to kinematics, which you did well on. So let's do a couple more example questions, and then we're done. So here, you and the bike weigh 100 kilograms, and you're towing a 30-kilogram trailer. The net force is 300 newtons. What's your acceleration? Well, acceleration is F net over mass. Now, I should say mass total, because this is 300 newtons over 100 kilograms plus 30 kilograms. I'd be surprised the number of people that miss that. 130 kilograms. And what is that? 2.31 meters per second squared. All right? Now, straightforwardish. Can we use that in another calculation? Yes. Now, I'm going to pause this here. I want you to go back and double check. Make certain you got this. Then I'm going to go do the two nasty, well, not nasty, but the two tricky questions you got to pay attention to. All right? So review this and then move on to the next video. Good luck.